OK, so no questions? OK, so then so this week, what we're going to do is complexity in algorithms. So last week, you heard a little bit how to build a quantum computer and kind of what the basic building blocks are, quantum gates and quantum circuits. And now we want to try to examine how you put together quantum circuits together into algorithms and how one quantifies how difficult a problem really is. And in particular, that last point is what I'm going to concentrate on today. Mostly I'll be talking about classical complexity, but also want to talk about quantum complexity a bit as well, of course. So complexity theory in the computer science sense, anyway, is basically the study of how difficult computational problems are. And in particular, what we'd like to do is we'd like to classify hard problems versus easy problems. But when you start to look at this question in a bit more detail, it's not exactly clear what it means. So what does it mean for a computational problem, to be hard versus easy, right? I mean, you could say, well, I don't know, there's some long amount of time t. And if the problem takes longer than time t to solve, then it's a hard problem. And if it takes less than time t, then it's an easy problem. OK, so at first sight, that seems like a reasonable cutoff. I mean, obviously, t is going to be somewhat arbitrary. But if you think about it, there's at least one really big problem with that, which is that whether, based on that definition, whether a problem is hard or easy depends on what computer you're running it on. Right? If you're running it on an old 10-year-old computer, obviously, just exactly the same problem, exactly the same algorithm is going to take much longer than if you run it on a modern, much faster computer. And that's a bit unsatisfying, because we want to classify whether the problems are hard or easy, not whether our computer is a fast or a slow one. We know kind of when our computer is fast or slow. And it's a much more subtle question of when the problem is. So what we'd like to do is we'd like to come up with definitions that are machine independent. So if the running time is not the right thing to look at, maybe we should look at the number of computational steps, right? Say the number of gates in the circuit that are needed to solve this problem. OK, and that's much better, because it kind of eliminates just general questions about the speed of the machine. But if you think about it some more, there's still a little bit of uncertainty here, right? And a little bit of machine dependence, because if you think of one universal gate set versus a different universal gate set, maybe one universal gate set can solve this problem in a few more or requires a few more computational steps than the other one, right? I mean, if you have to build your Toffoli gate out of pi over 8 gates, this is a quantum example, pi over 8 gates and Hadamard gates versus just using the Toffoli gate by itself, that might make it a little bit slower, right, in terms of requiring a few more computational steps. And so that's still some machine dependence there. Now, that's kind of a small thing. You can get rid of that. But there's actually, if you think about this a bit more, you'll find a totally different class of problem, which is that problem with the definition, which is that given any particular question, right, there's always going to be a very quick program that outputs the answer, right? Because any question has some answer, which is just going to be I mean, if it's a yes or no question, it's just one bit output. And so you can just write a program that will output yes. OK? So if you think of what is the shortest program that gives the answer to this particular question, the answer will always be, well, it just outputs this one bit. Okay, now clearly that's cheating, right? You don't want a program that only answers this one question. You want a program that answers a class of questions. And so that's the next thing that we have to put into this definition. So we want a machine-independent definition, and we can't talk about the complexity of just a single problem. We want to talk about the complexity of classes of problems or sets of problems. And normally, of course, we're going to talk about sets of related problems. You know, well, OK. I'll give you an example in a little bit. OK. Yeah. So OK. So here actually is a good example, a good place to give the example. And so the example I'm going to be using for a little bit is primality testing. So primality testing, you're given as input an integer, I guess a positive integer. And you're supposed to answer the question, is x prime? Okay? So here you see this is a related class of problems. For any given x, again, it's just one-bit answer, yes or no. But when you run over all possible x's, then it's a big class of problems, and we're actually can meaningfully talk about the complexity of this problem. OK, so in order to do so, let's see, a little bit of space maybe. So in order to do so, let me make some basic definitions. So this is notation. So this obviously is the set of 0 and 1. And when I put the star up here, it's the set of bit strings of arbitrary length. And then this absolute value notation gives the length of a bit string. So then the computer science terminology for problem is, at least a yes-no problem, is a language. And language is just a subset of all possible bit strings. OK. So this seems like a kind of mysterious definition, why a language should just be a subset of bit strings. And why I say that's a problem. Well, so the interpretation here is that we're talking about a decision problem. Which is a yes-no problem. So we're asking a question like primality testing that has an answer yes or no for various kinds of inputs. And the yes instances, so the inputs that have the answer yes are in the language. And the inputs with the answer no are not. OK, so now you can see why a subset actually corresponds to a function, right? It's a subset that gives you all the yes answers, and then the the no answers are just the other ones. Okay? So does this make sense?
Why do we call it a language?
I don't really know. That's a historical thing from the. I mean, it's. Yeah.
So this has got
it's from the early days of computer science.
This has got nothing to do with like the language of programming like that.
Not with programming languages. Well, it might in some sort of, again, historical way. I mean, there's certain languages, programming languages, that you can kind of express a little bit more like this. If they're making kind of true statements, and you kind of build up true statements with longer and longer strings. And so there may actually be some sort of historical connection there. The other thing is, I mean, it also relates a little bit to language as in what we speak, in the same sense that there's kind of formal languages of some. So for instance, you can say some sentences are grammatically allowed in the language and some are not. So you can think of that at a formal level of, again, as a subset of a string of characters. And you can kind of write down, I mean, in these formal languages, you can write down formal rules that say some of what is allowed. Yeah?
Are we okay with it being like countably infinite, this set?
Yes, yes. In fact, that's what we want. Because if it's not countably infinite, so there's only, it's not, well, okay, so it's, I mean, so, okay, so if there's only a finite, if the language is only finite, then it's always going to end up being kind of easy for the reason that I said before. So if there's only one example, one thing in this language, then you can just check if that's the input that you have, and if so, output yes, otherwise you output no. And if there's only a finite things, then you just go through the list. Okay, so that might take a long time if it's a big list, but it's just a constant. And as we'll see in a moment, what we're really interested in is the scaling. Okay. So are there other questions? Otherwise, I can just go on to that part of the definition. Yeah?
So am I right in thinking about basically like this is, we want to find a set, we have a bit strings of words, and we've got like a decision problem to the dictionary or something like that?
Yeah, so again, if it's a finite set, then it really is just a dictionary.
Right.
You look up the valid words,
yeah.
And anything that's not in the dictionary is considered invalid.
Yeah.
When it becomes infinite, that's no longer such a good way of approaching it. You need some more clever approach. Okay? And this is an example, of course, of something of an infinite language, right? So the things in the language, so the primes language is the set of prime numbers, right? Which, of course, famously, using one of those ancient Greek proofs, is infinite. Yeah.
Just to be clear, 0, 1 star is the set of finite strings?
Yeah, that's right. Yeah, so of arbitrary length, I guess.
Very fine. Thank you.
Okay. Okay, so then let me move on. So more definitions. So we say that an algorithm, which I guess I'm not going to define, but I could informally if you need it. We say that this algorithm decides a language L if for all bit strings a of x is equal to 0, which I interpret as no, if x is not in L, and a A of x equals 1, yes, if x is in L. And then we say, in either case, we say that x is an instance. It's the word I tried to use before but hadn't defined yet, of L. And you either say it's a yes instance or no instance, depending on which case you're in. And sometimes actually we talk about promise problems. So that terminology simply means that the instances are drawn from some proper subset. So primality testing is not a promise problem because the instances are all positive integers, right? And so any bit string can be interpreted as a positive integer. The yes instances are the prime numbers. The no instances are the composite numbers. And I guess depending how you define it, one could be in either category. So maybe a very brief example of a promise problem. So later on, we'll be talking about factoring. It's an important problem. Factoring, it doesn't have to be a promise problem either. But one special case of factoring that we're interested in is factoring numbers which are a product of two primes. Okay? And there you do kind of have a promise, right? That the input that you're getting is always going to be a product of two primes. Okay? And maybe your goal is to find out, is there a prime factor below some value to make it a decision problem. Okay, so this is just terminology, but does it make sense so far?
Question.
Yeah.
The statement x is an instance of L is only for A of x equals 1.
No. So x is an instance of L in either case. So x is an instance. So okay. So when you don't have a promise problem, any bit string is kind of an instance of L. But it's mostly a matter of interpretation, whether you're thinking of it as a possibility of being in L or not. Okay. So you have the yes instances where x is in L, and the no instances where x is not in L. Now, in a promise problem, then there is a real meaning here, in that the instances are only things that satisfy the promise, that are in this subset. Yeah.
Does the elements of the, in a promise problem, does the elements that aren't in the subset have to be like infinite?
No, the promise could really be anything. I mean, usually there's not much point in doing it if there's only a finite number of things that don't satisfy the promise. I mean, so primality testing, right? You could say, well, I'll promise you that it's not 1, because 1 is kind of a weird special case.
Yeah.
But, what's really the point, right? You can either put 1 in the language or put it not in the language and just treat it as some exception. And it doesn't substantially change the complexity of any kind of algorithm that you're going to use. Yeah?
So you're assuming that algorithms always hold?
No. Right, so that's a good question. I don't assume that, but if it doesn't halt on all instances, it's not the language. No, so this is just about a particular algorithm. Okay, but if this particular algorithm doesn't halt for this language on all instances, then it's not deciding the language. Okay.
Why do you say that it decides the language when really it's deciding if
Yeah.
the value is
Again, this is, I guess, historical terminology. But basically, it's short for deciding whether the instances are in the language or not. I mean, there's all sorts of intermediate stuff, but yeah. Okay? So, a simple example, going back to primality testing. So what's an algorithm that decides primality testing? Well, here's an algorithm. It's not a particularly good one, but it's easy to write down, which is algorithm. So we'll run through all y that are between 1 and x, and try dividing y into x. And of course, if y does divide x, then halt and output no, because x is clearly not prime. And if we reach the end, then we output yes. Okay? So everyone agrees that this algorithm decides this language, I hope. Okay? Right. So as I said, this is not a particularly good algorithm. So how long does it take to run? Well, we have, in the worst case, we have to try, I mean, in the case where it's a prime number, we have to try basically x different values of y. And each time we divide y into x, that takes, well, y is, well, so x is log x bits long, log base 2. And y could be up to log x bits long. And I believe if you kind of run long division, that'll take a time that's about the product of the length of y with the length of x. So it's about potentially up to log x squared time. And we have to do x of those. So, so the time, meaning the number of steps, is roughly x log squared x. Okay. And the input size is log x, right? Because the input is x, the instance size. And so that's what that's saying is that this algorithm runs in a time that's exponential in the input size, okay, in the instance size. So that's pretty bad. That means that as x gets larger and larger, but still reasonable to write down, you know, it's easy to write down a 100-bit number. But running this algorithm for a 100-bit number is going to take way too long. Okay? In fact, there are much better algorithms for primality testing, which I'm not going to go into. But this is just to give you an example of the sort of calculation we want to do. Okay. So in that calculation, I guess one thing that's worth pointing out is I talked about the time it took when we had a prime number, right? Because that's the longest case. Obviously, sometimes that algorithm will be very fast, right? If you have an even number, then it'll end very quickly. Okay. But what I'm going to be talking about is the worst case complexity. And so people do talk about other things, but this is kind of the most common and average case complexity. It can be kind of complicated. So in worst case complexity, so first of all, I insist that the algorithm works on all inputs. So on all instances. And I'm going to take the time, the complexity, for the worst possible input. Okay. So the advantage of worst case complexity is that when I calculate the worst case complexity, I know that if I run that long, I will get an answer, right? Whereas if you say, well, most of the time, half the numbers here end very quickly, and the numbers divisible by 3, they also end very quickly. So most numbers for primality testing will be very quick, because very quickly you'll find that they're not prime. But that's kind of beside the point of primality testing. Primality testing, you really want to try everything to make sure that it really is prime or not. OK, so and of course, when we want to talk about the complexity of a language, we're going to take not just the first algorithm we thought up, like in the case of primality testing, but we want to take the best. So the complexity of the language is going to be the complexity of the best algorithm that decides the language. And again, this is the best worst case complexity for the algorithm. So we take the best over algorithms of the worst over inputs. OK, and as I mentioned, we're interested in the scaling. So how does the complexity depend on the instance size? And this is to get rid of this problem of, well, we could just have some big lookup table that calculates for a finite set of inputs. This is really telling us how the complexity changes as we go to very large sizes, which is really telling us kind of how involved the problem is. We're separating out cases where the problem takes a long time because there's a lot of inputs versus problems that take a long time because it's actually a very complicated calculation that we have to do. OK, but we're not quite done. So one thing to note is we still want to get rid of that machine dependence, right? So if we calculate the exact number of steps, then, for instance, we have this problem of, well, one universal gate set versus another universal gate set might take a different number of steps. So what we're going to do is we're going to ignore constant factors. So in support of this, there's another definition. Again, this is terminology. And so we use what's called big O notation. And so big O notation says that a function f of n is big O of some other function g of n if there exists constant c such that f of n is less than or equal to c g of n for all n. Okay? So this is getting rid of those constant factors. We can talk about, so up there I said it was about log, x log squared x was the running time of that algorithm. So using this notation, so what does the about mean? Well, there's various things I left out. I didn't say exactly what the time for multiplication was. And there's probably a half or something because a lot of the numbers are actually shorter than that, so it takes less time to divide them. So really what I meant up there was that the running time is O of x log squared x. Okay, so that's how we use that to get rid of those constant factors. Okay? Is everyone okay with this so far? Okay, but even getting rid of the constant factors actually doesn't get rid of the machine dependence. Yeah, so I haven't really talked about different models of computation, but there are a lot of different models of computation. So for instance, I talked about the circuit model, but there's also a Turing machine model and a variety of other things. Even within the circuit model, you can think of, say, circuits with the bits arranged in 1 dimension or 2 dimensions or 3 dimensions, or just allowing gates between any pair of bits. And when you do that, when you can think of these different models of computation, what you'll find is that it's not just constant factors between them. Sometimes it's worse than that. Sometimes different models of computation may differ by polynomial factors. So if we have something that's O of G of X in one model of computation, then in another model of computation, it might be O of some polynomial of G of X, or sometimes G of poly X. Did I get 1, 2, 3, 1, 2, 3? Okay, so really when we talk about complexity, we want to have things that not just ignore constant factors, but ignore polynomial blow-ups as well. And so bearing that in mind, we're finally ready to actually define a complexity class. Yeah?
Polynomial of any degree.
Of any degree, that's right. And the reason for that, well, okay, I mean, so yeah, so most of the different models that people will talk about will not differ by arbitrary degree polynomials. There'll be linear factors or quadratic, maybe. Maybe third order, but generally not. The thing is that we'd like to have something where we don't have to worry about that at all. And it's much more straightforward to do that. I mean, let me write down the definition, and then let me just answer that question again. So, okay, so the definition of a complexity class is simply a set of languages. But one particular very interesting example of a complexity class is P, which stands for polynomial. And P is the set of languages which can be decided in time f of x for some polynomial x, some polynomial f. Okay, so to get back to your question, so this is any polynomial. This could be n to the 780 if that's what you find. The thing is that this class is robust under polynomial changes. Okay, and if you just said, well, okay, I only care about polynomial changes up to quadratic, then it becomes much harder to draw a nice line here, right? You might also say, well, n to the 780, that's crazy. I would never want to run an algorithm that actually takes that long. So let me cut it off and say, n to the 5th. Maybe that's going to be in my class P. But of course, then if I go to another machine, that's n to the 10th, right? And so maybe I should actually be drawing the line n to the 10th But you see, then I would have to say which machine it's going to be on, right? Whether it's going to be on the fast machine or the slow machine. And maybe there's a machine I haven't thought of that's a little bit faster, a little bit slower. And so it's just much simpler and much cleaner to draw the line and say polynomial. And then all of these different things will vary by polynomials, but they'll still give us the same complexity class P, no matter what machine we're talking about. OK? Yeah?
Don't we want to have like O of f of x? Definition of-
Yes, but the O is kind of absorbed in the fact that it's any polynomial, right? So n to the 780 is a polynomial, but so is 1,000 times n to the 780. Okay, and both of them are O of n to the 780, but it's the same. I mean, it would give the same answer.
Oh, so in time you mean within that bound? Exactly that time. That's why
Yes, that's right. That's right. It doesn't have to be exactly that time. First of all, on different inputs, it can take different amounts of time. But I guess you're right that that's something that runs in time n to the 1.5, and there are such algorithms. Doesn't run exactly a polynomial time, but it's still considered in here. So yeah, you're right. It's in time at most. Okay. Okay. So we say that languages in P these are the easy ones. In this case, I mean easy for a classical computer. Ones not in P are the hard ones. We say a polynomial time algorithm is an efficient algorithm. Okay. Okay, so that algorithm that I gave you up there for primality testing, that's not an efficient algorithm, right? Because as I said, it takes exponential time in the input. But it turns out, and this is not at all obvious, that there is a polynomial time for primality testing. But it's not something that's really easy to find. In fact, it wasn't discovered until 2002, even though this is a problem that a lot of people have been interested in and worked on. So that's just to give you an example of a case where it's not obvious that a language is in P, but actually it is in P. But maybe that gets you thinking along the right lines for the next comment, which is that there are languages that are not in P. There are languages where the best algorithm, and I'm not just talking about the best known algorithm, but actually the best algorithm to solve them takes a time that's exponential in the size of the input. Okay? And if you watch lots of movies, you may get the impression that a sufficiently brilliant computer programmer can solve any computational problem. But it's not true, actually. There's some problems that are just too hard to be solved, that there's no efficient algorithm to solve them. And actually, there's something that's much more profound that one can say, because there's some problems which not only cannot be solved efficiently, they cannot be solved at all. So these are the undecidable problems. So undecidable problems have no algorithm that decides them. And so the kind of the standard example of an undecidable problem is the halting problem. So the halting problem says, I give you a description of a computer program, the code for it, and I'll give you an input, and I want to know, does this program running on this input halt ever? Okay? I don't want to know. So the question, does it halt after 10,000 steps? That's a decidable problem. I just run the program for 10,000 steps, and then I'll see whether it's halted or not. But the question of, does it ever halt? Well, certainly you can't answer as easily as that, right? Because if you run it for 10,000 steps and it hasn't halted, well, maybe it's going to halt at step 10,001. You don't know. Or maybe it's step million that it halts, or a billion. So if you keep on running it and it hasn't halted, you still don't know if it's going to halt or not. Yeah?
Sorry, I'm not clear on the statement of the problem.
Yeah.
You might as well look for a halt command inside the program.
Well, no. So the point is there might be some loop. So you could have a halt command written in that code, but maybe there's some loop that never ends. And so it never, it's a while loop that says, while this is true, do this. But the thing is always true, so it keeps on going. Okay? And so even though it halts after the while loop finishes, it never finishes the while loop. That's an example of what can happen. Okay? And so I mean, I said that running the program is not a sufficient way to decide this, but of course there could be something much more subtle. But you can prove, this was one of Turing's great discoveries, you can prove, in fact, that there is no algorithm to decide the halting problem. Not no efficient algorithm, no algorithm at all. OK, so that's fairly shocking, although it's had decades to permeate into the popular consciousness. But if you start to plug that insight back into the questions we've been talking about so far, it might make you a little bit worried. Right? I said I wanted a machine-independent method of classifying the complexity of problems. But before I do that, I should be sure, for instance, that all machines can decide the same class of problems. Right? What if this halting problem is undecidable on a computer based on circuits, but some other model, Turing machine or something else, can decide that problem, right? Then talking about complexity is a little bit beside the point, because I've totally ruined the notion of what algorithms decide what problems, because it's different on different machines. But that appears not to be the case. So there's something called the Kirch-Turing thesis. And the Kirch-Turing thesis says that all physically reasonable models of computation decide the same set of functions, or the same set of languages. Okay? Now, this physically reasonable is kind of weird from a computer science perspective, although for a physicist, I guess it seems reasonable. And it's really necessary, because people have come up with all sorts of crazy models of computation. And some of them can actually solve undecidable problems. So for instance, if you have an analog computer, where you're no longer working with bits, but continuous variables in the memory, and this analog computer has infinite precision. Turns out that a computer like this can actually solve some undecidable problems. Okay? But of course, it's not physically reasonable, because infinite precision, that's not reasonable. And to bring back to the topic of this class, you might worry about quantum computers, right? So that's a different model of computation. It's outside what people normally think about. But it turns out that quantum computers actually do decide the same set of problems, assuming, again, you don't assume infinite precision of some sort. So how can you decide? So given a quantum algorithm, so you have some quantum circuit, how on a classical computer could you decide what the output of that is going to be? Well, each quantum gate you can write down as a matrix. It's acting on an n-qubit Hilbert space. So that's a 2 to the n dimensional Hilbert space. So it's 2 to the n by 2 to the n matrix. OK, so that's big. But it's something that you can write down. And you multiply these out. OK? And then you'll get the overall unitary that this thing does. And you look at the appropriate matrix element to figure out what the probability of, say, a 0 output is going to be. Or maybe you have to add up a bunch. In any case, you can do that, right? It's just some very long computation. I guess there's one thing you have to be careful about, which is the amplitudes. Again, they have potentially infinite precision. But you can't measure that in a quantum computer anyway, right? Because when you measure probability of one outcome, you're only getting an approximation to the actual amplitude. Okay. So if you plug that in, you say, well, I run the quantum computer so many times, I can only calculate probabilities to this many digits, and so I only need to keep track of that many digits when I'm multiplying these matrices together. Yeah?
Just a quick clarification. This says nothing about which complexity class they're in, right? So
that's right. So this is just whether they decide or not. Right. So it's the complexity class of decidable versus undecidable.
So a quantum computer might do it faster, but it
that's right.
do the same set of problems.
That's right. And certainly the way that I just said of doing it means that there'll be not just a polynomial blow-up for the quantum computer, but an exponential blow-up when you go from a quantum algorithm to a classical algorithm. So that's the next thing we need to worry about. So before people started to work on quantum computation, there was a refinement of this Church-Turing thesis, which was intended to kind of make sense of complexity theory, and was based on this observation that these different models of computation that people had thought of really, in the past, only really did differ by polynomial factors. And so they had what's sometimes called the strong Church-Turing thesis. And that says that the complexity of languages differs by only polynomial factors between physically reasonable. Well, maybe I should say on physically reasonable. In physically reasonable models of computation.
Wait. Does that mean that quantum computation can't solve something fast an exponential time if you can't do it with classical computation?
Well, if it were true, it would mean that.
Okay.
And so this is one of the kind of profound philosophical impacts of quantum computing for classical computer science. So quantum computers seem to violate this strong Church-Turing thesis. Okay? And that, of course, is what I'll be talking about for most of the rest of the week. Well, at least for part of the week. And to the extent, I mean, there's a small number, I think a small number, but there's certainly some classical computer scientists who are so devoted to the strong Church-Turing thesis that they refuse to believe that quantum computers can work. Either there's actually some efficient classical algorithm that will simulate quantum computation, which is possible, or they think there's something wrong with the model that somehow they can't actually be built, something like that. But this is really a big deal, right? This means that while we can classify the complexity of problems without worrying about what machine, mostly we do have to worry about whether it's a quantum machine or a classical machine. We're going to get a different complexity class for quantum algorithms than for classical algorithms.
So this is not actually proven.
No, in fact, none of these. This other Church-Turing thesis is not proven as well.
Okay.
And if you look at it, how can it be proven, right? It says all physically reasonable models of computation. That's an undefined term. What's a physically reasonable model of computation?
Something that decides the same set of languages.
Well, I suppose in that case it becomes a definition rather than a. But clearly that's not right either, right? Because there's also going to be some physically unreasonable models of computation that decide the same set of languages.
Mm-hmm.
So it's not a great definition even if you want to use it as definition. And it's particularly not a great definition when you start to apply it to the strong Church-Turing thesis, and you run into the possibility that people could actually build things that you decided were physically unreasonable. Okay. Okay. So let me just put up one more Church-Turing thesis, which is the quantum Church-Turing thesis. So, of course, if quantum computers violate the strong Church-Turing thesis, then we have this breakdown of complexity theory. We have to have quantum versions of the complexity classes and classical versions. But it opens the possibility that different kinds of quantum computers could do different things as well. And that appears not to be the case. And so the strong Church-Turing thesis basically says that yes, there's quantum complexity classes, but we don't have to worry about anything more. And so, again, this physically reasonable computer comes up. And we'd like to say that any physically reasonable model of computation can be simulated in polynomial time on a quantum computer. Okay. Now, it's certainly possible, based on our experience with quantum computers, that there will be some other kinds of model of computation, I don't know, string theory computer, black hole computer, something like that, that brings in new laws of physics that let us actually do better than a quantum computer. But for the moment, this seems to be the case. Certainly anything that anyone is imagining building today seems to fall in this category. You'll occasionally see claims to the contrary, but usually they're either just blatantly wrong or run afoul of this physically reasonable part. OK, so let me end then with one last definition. So we talked about the complexity class P. So that's a set of things that can be done efficiently on a classical computer, the easy problems for a classical computer. And now, as I've told you, we need a different complexity class when we're talking about quantum computers. So that one is called BQP. And BQP is a set of languages and for these languages, there's supposed to exist a quantum algorithm and we want this algorithm to have the following properties. So first of all, it should run in polynomial time. And since it's a quantum algorithm, it only runs on a quantum computer. So I'm not going to stick in the word quantum anymore. And OK, so when x is a yes instance, we want this algorithm to output yes. But because probabilistic, right, a quantum algorithm is probabilistic, we we don't insist that it output yes with 100% probability, just with a very good probability. So if x is an L, then it outputs yes with a probability that's at least 2/3. And if it's not an L, if the input is not an L, then it should output no with probability at least 2/3.
Why 2/3?
Why 2/3? Well, 2/3 is just some convenient number. Picking probability 1 is too restrictive because it doesn't allow for probabilistic algorithms. If I pick, say, 9/10, right, that'll work just as well. The thing is that if I have an algorithm that succeeds with probability 2/3, and I run it twice, or 3 times, or 10 times, I will increase my confidence that it's correct, right? And so by taking the majority of those 10 runs, I will get an algorithm which is still polynomial time because I've only multiplied by 10, but I'll give one that outputs yes with probability greater than or equals some number that's larger than 2/3. And here's, again, some number that's larger than 2/3. Okay? And that's true for any constant, right? Whatever the constant is here, provided it's between 1/2 and 1, strictly between 1/2 and 1, I can magnify it, make it closer to 1 by repeating. Okay? So 2/3 doesn't really matter. It's just some convenient thing. And it's kind of nice and symmetric because it's, this is also saying that it's outputting yes with probability at most 1/3. So it's 1/3, 2/3 is the distinction.
So if, in other words, if we change that probability to be anything strictly greater than 1/2,
yeah,
it wouldn't change the set of languages.
That's right.
So
that's right.
So
this is this is for definiteness, and that sort of thing is the sort of property that we like out of complexity classes, that it's not sensitive to small changes in the definition, like changing this constant. Okay? And so this is, again, why we wanted to, in the definition of P, we wanted to say polynomial time rather than n to the 5th, right? Because if it's n to the 5th and we change to a slightly different model of computation, or we change that n to the 5th to the n to the 6th, it changes the definition of the complexity class. So again, we want something that's robust. So now let me point out that it doesn't even have to be a constant. You could use a 1/2 plus some function of n. But if that function of n is 2 to the minus n, so if it's a 1/2 plus 2 to the minus n that it's supposed to succeed with, well, then it would be a valid definition. I mean, it's a complexity class that you can define that way. But it would be one that's hard to run in practice. Because in order to figure out, I mean, if you run it and it has success probability 2/3, then you only have to run it a few times before you're pretty sure you're getting the right answer. But if it's a 1/2 plus 2 to the minus n, then you have to run it maybe 2 to the n times before you can figure out whether it's actually a 1/2, whether it's greater than a 1/2 plus 2 to the minus n or less. And then it wouldn't be polynomial time anymore, right? Because you're repeating an exponential number of times. Right. And so, I mean, these complexity class languages, you couldn't necessarily read too much into the letters that appear in them. But they do have meanings, not always sensible ones. But the P here is polynomial, so that makes sense. The Q is clearly quantum. And the B is bounded. And that stands for bounded probability. So that's why we're separating out these probabilities like this. Okay? Okay, so are there questions on this, on BQP or any of the other stuff today? Yeah?
It seems a bit unfair to compare that with P, because P has to give the right answer all the time.
Yeah. So, so there is a classical complexity class called BPP, and the extra P is probabilistic. The B is again bounded, And it's the same as this definition, but without the quantum. So it just says classical algorithm. Okay. However, the widespread belief nowadays is that P is actually equal to BPP. Okay. Doesn't have to be true, but people seem to believe that. But you're right, that really the fair thing to do is compare BQP with BPP. But we still think it's the case that BQP can solve various problems, certainly that we don't know how to solve in BPP. That's definitely the case.
So we don't know how to do factoring in BQP.
For instance, yeah. Yeah.
When you say that P is equal to BQP.
No. P,
Okay.
people believe that P is equal to BPP.
Oh, okay.
BQP is probably bigger.
Also, I'm not sure I understand the quantum Church-Turing thesis. Like
Sure.
polynomial time in what? On the size of the input?
Yeah. So it's always in the size of the input. But the quantum size. So if you have, so depending on the system, it can be a bit hard to quantify the resources properly. Certainly, if you have something that breaks up into qubits, then you can say, oh, well, I have this many qubits and this many gates, or whatever you're using instead of gates. And then you want polynomial time in terms of those numbers. If you have something more complicated, like anyons, that you're braiding on a billion anyons, well, in there you want to count the number of anyons and the number of crossings you do. So that's another issue that appears in all of these Church-Turing versions, which is how do you quantify the resources that you're using? So for instance, here's another physically unreasonable model of computation. I will, in this model of computation, I will do some gates. Let's say I'll just do one gate, and it takes a time 1. And the next gate I do takes a time 1/2. And the next one I do takes a time 1/4, and so on. And so I can do an infinite number of gates in this model in a finite amount of time, right? But it's unreasonable, obviously, because it requires arbitrarily fast gates. And if you look into it, one way that you could imagine doing this is to put more and more energy into each gate to make it go faster and faster. But then you're saying, well, I need an infinite amount of energy to run this computer. And so you really have to think about everything that goes into the computer and count the resources properly in order to make it work. And sometimes that's quite subtle. Okay.
Currently, the stabilizer space is only known to, it lies within P, but it could strictly be equal. Is that right?
Sorry, what do you mean?
Your stabilizer space.
Yeah, so that's actually, well, it depends how you define it, but that's strictly less.
Strictly less than.
Yeah.
Oh, okay. Interesting.
Okay. Maybe that's enough for today. You can still ask questions tomorrow. We'll come back to talking about complexity theory, and if you have time, get into algorithms.
Jumping in.